time travel is real. Not in the sense of science fiction. You can't build a DeLorean, hit 88 miles per hour, and visit 1955. You can't go backward in time. That remains impossible as far as we know, forbidden by causality and the laws of physics. But traveling to the future, that's happening right now, every second of every day. Not as speculation, as confirmed, measured, tested reality. Astronauts on the International Space Station are traveling to the future. GPS satellites orbiting Earth are traveling to the future. Particles in accelerators are traveling to the future. And if you've ever flown on an airplane, you've traveled to the future too, just by an amount too small to notice. I'm Leonard Susskind, and I'm going to explain why time travel to the future is not only possible but routine, why it follows directly from Einstein's theory of relativity, why we've measured it to extraordinary precision, and why, if you had enough energy and the right spacecraft, you could travel thousands of years into Earth's future while experiencing only a few years of your own time. Let me show you how. Start with Einstein's great insight. Time is not absolute. There is no universal clock ticking away the same seconds for everyone in the universe. Time is relative. It depends on how fast you're moving and how deep you are in a gravitational field. Two observers moving at different speeds will measure time differently. Their clocks tick at different rates. Neither is wrong. Both are correct from their own perspective. But when they compare clocks afterward, they'll find that different amounts of time have passed. This is called time dilation, and it's the mechanism of time travel to the future. Let me make this precise with an example. You're on Earth. Your twin gets in a spacecraft and accelerates to 99.9% the speed of light. She travels for what feels like 1 year to her, then turns around and comes back. When she returns and steps off the spacecraft, how much time has passed on Earth? Not 2 years, 22 years. Your twin aged 1 year on the round trip. You aged 22 years waiting for her. She traveled to the future. When she left, the year was 2025. When she returns, according to Earth's calendar, it's 2047. She skipped forward in time. This is not a thought experiment. This is a direct consequence of special relativity, confirmed by every test we've ever performed. The faster you move, the slower your clock ticks relative to stationary observers. Move fast enough, and you can travel years, decades, centuries into the future while experiencing only days or weeks yourself. The math is precise. The time dilation factor is gamma equals 1 square root 1 v squared divided by c squared, where v is your velocity and c is the speed of light. At 99.9% light speed, gamma is about 22. Every second that passes for you, 22 seconds pass for the stationary observer. At 99.99% light speed, gamma is about 70. At 99.9999% light speed, gamma is about 700. Get close enough to the speed of light, and you can travel as far into the future as you want. The limit is not physics, it's engineering. You need enormous energy to accelerate to those speeds. But in principle, time travel to the future is unlimited. You could leave Earth in 2025, travel for 10 years of your own time, and return to Earth in the year 12,025. 10,000 years would have passed on Earth. You'd step out of your spacecraft into a world utterly transformed, unrecognizable, while you aged only a decade. This is one-way time travel. You can go to the future, you can never come back. The past is gone, unreachable, but the future is open. And physics lets you get there as fast as you want, limited only by how much energy you can muster. Now let me show you that this is already happening. Not science fiction, not speculation, measured reality. Muons are unstable particles created when cosmic rays hit Earth's upper atmosphere. A muon at rest decays in about 2.2 microseconds. That's 2.2 millionths of a second, At the speed they're created, typically 99.9% the speed of light, they should travel about 660 meters before decaying. They're created at altitudes of 10 to 15 kilometers. They shouldn't reach the ground. They should decay in the atmosphere. But they don't. Muons reach the ground routinely. We detect them at sea level all the time. Why? Because from our reference frame, the muons are time dilated. Their clocks run slow. A muon moving at 99.9% light speed experiences a time dilation factor of about 22. From our perspective, it lives 22 times longer, about 50 microseconds instead of 2.2 microseconds. That's enough time to travel 15 kilometers and reach the ground. From the muon's perspective, it lives only 2.2 microseconds. But the atmosphere is length contracted. The 15 kilometers of atmosphere is compressed to less than 700 meters in the muon's frame, so it crosses the distance before decaying. Both perspectives are correct. Both predict the muon reaches the ground. Time dilation and length contraction are two sides of the same relativistic effect, and the muon has traveled to the future. It experiences 2.2 microseconds. Earth experiences 50 microseconds. The muon has skipped ahead in time. This is measured every day. Muons are time travelers. Now let me tell you about GPS satellites, because this is where time travel becomes essential technology. GPS satellites orbit at an altitude of about 20,000 kilometers, moving at about 14,000 kilometers per hour. At that speed, special relativity says their clocks should run slow compared to clocks on Earth's surface by about 7 microseconds per day. They're moving fast, so time dilation slows their clocks. But there's another effect. General relativity. Gravity also affects time. The deeper you are in a gravitational field, the slower your clock ticks. The GPS satellites are higher in Earth's gravitational field than we are. They're in a weaker field, so their clocks run faster than ours by about 45 microseconds per day. Combine both effects. The satellites' clocks run faster than Earth clocks by 38 microseconds per day. That's 38 millionths of a second per day. Sounds tiny. But GPS works by measuring the time it takes for signals to travel from satellites to your receiver. Light travels about 300 meters per microsecond. So a 38 microsecond error accumulates to an 1 kilometer position error per day. Without correcting for relativity, GPS would be useless within hours. Every GPS satellite has this correction built in. The clocks are programmed to tick at a slightly different rate to compensate for relativistic effects. Your phone's navigation works because engineers accounted for time travel. You are navigating using relativity every time you use GPS. The satellites are experiencing time differently than you are. They're traveling to the future faster than you are because they're higher in the gravitational field and moving at orbital speeds. The difference is tiny microseconds per day, but it's real, measurable, and must be corrected for. Now let me tell you about the Hoffele-Keating experiment, because this is the most direct test of time travel we've done. In 1971, physicists Joseph Hoffele and Richard Keating flew atomic clocks around the world on commercial airliners. Some clocks flew eastward in the direction of Earth's rotation. Some flew westward against the rotation. Some stayed on the ground as controls. When the clocks returned, they had measured different amounts of time. The eastward clocks lost about 59 nanoseconds compared to the ground clocks. The westward clocks gained about 273 nanoseconds. The differences matched the predictions of special and general relativity to within experimental uncertainty. The airplanes were time machines. The clocks aboard them traveled to the future at different rates depending on their speed and altitude, not by much nanoseconds over the course of days. But the effect was real and measured. You've time traveled if you've ever flown. Not enough to notice you'd need to fly continuously for thousands of years to age even 1 second less than people on the ground. But the effect is there. Every airplane passenger is a time traveler. Now let me address the twin paradox, because this is where people get confused. You and your twin start on Earth, the same age. Your twin gets in a spacecraft, accelerates to high speed, travels to a distant star, turns around, and comes back. When she returns, you've aged more than she has. She traveled to the future. But here's the supposed paradox. From her perspective, you were the one moving. Special relativity says motion is relative. So why doesn't she see you as the one who time traveled? Why isn't the situation symmetric? The answer: acceleration breaks the symmetry. Your twin accelerated when leaving Earth, decelerated when reaching the star, accelerated when turning around, and decelerated when returning to Earth. She felt forces. She had to fire rockets. Her reference frame was not inertial. It changed direction. You, sitting on Earth, never accelerated significantly. You remained in an approximately inertial frame the whole time. The situation is not symmetric. And special relativity, properly applied, including the effects of acceleration, predicts unambiguously that your twin aged less. She's younger when she returns. She time traveled to the future. This has been confirmed experimentally with particles in accelerators. Unstable particles that decay quickly at rest live much longer when accelerated to high speeds. The particles in the accelerator's reference frame don't age slower from their perspective. They live their normal lifespan. But from our perspective in the lab, they're time dilated. They exist longer. They travel to the future. Now, let me tell you about the limits. Can you travel to the future arbitrarily far? In principle, yes. There's no limit except energy. Accelerate to 99.9999999% the speed of light, and you can skip millennia into the future while aging only years. The faster you go, the greater the time dilation. Approach the speed of light asymptotically, and you can travel as far into the future as you want. But you can never reach the speed of light. That would require infinite energy, and you can never go backward in time. The past is causally closed. Special relativity forbids it. Every path through space-time that respects causality is future-directed. You can only move forward. Or can you? General relativity opens a loophole. In curved space-time under extreme conditions, closed time-like curves might exist paths through space-time that loop back on themselves, returning to an earlier time. These appear in certain solutions to Einstein's equations: rotating black holes, traversable wormholes, exotic spacetimes with strange topologies. But every time we find a closed time-like curve in the equations, something goes wrong. The wormhole requires exotic matter with negative energy density that probably doesn't exist. The rotating black hole's interior is unstable and destroys anything that enters. The exotic space-time requires conditions we can't create and probably violate quantum mechanics in catastrophic ways. Stephen Hawking proposed the chronology protection conjecture. The laws of physics conspire to prevent time travel to the past. Whenever you try to build a time machine, quantum effects or classical instabilities destroy it. Nature protects causality. The universe won't let you go back and kill your grandfather. We don't have a proof of this. But every attempt to construct a viable time machine has failed. General relativity allows closed time-like curves mathematically, but physics seems to forbid them in practice. So forward time travel is easy. Backward time travel is almost certainly impossible. Now, let me address something philosophical. If time travel to the future is real and happening constantly, why doesn't it feel strange? Because we're all traveling to the future at the same rate, 1 second per second when we're at rest, relative to each other. Time dilation only becomes noticeable when there are large velocity differences or strong gravitational fields. In everyday life, you and the people around you are moving at nearly the same speed. You're all deep in Earth's gravitational field at nearly the same depth, so your clocks tick at nearly the same rate. You age together, you experience time together. It's only when someone accelerates to high speed or climbs high in a gravitational field that the differences become measurable. And even then, they're tiny unless the speeds are relativistic or the fields are extreme. But make no mistake, you are moving through time right now, 1 second per second. And if you accelerate, if you move fast or climb high or orbit Earth, you move through time at a different rate. You'll travel to the future faster or slower than people at rest. Time is not a fixed background. It's dynamical, flexible, relative. And that flexibility is what makes time travel possible. Now let me tell you about the most extreme time travel scenario physics allows. Black holes. Near a black hole's event horizon, gravitational time dilation becomes so extreme that you could orbit just outside the horizon for a few hours of your own time while centuries pass in the universe beyond. This isn't speculation. This is what general relativity predicts. Imagine parking your spacecraft at a stable orbit just above the event horizon of a supermassive black hole, the kind at the center of galaxies, millions of times more massive than the Sun. The gravitational field is so strong that time runs dramatically slower for you than for distant observers. You orbit for what feels like 1 year. When you return to Earth, 10,000 years have passed. You've traveled 10 millennia into the future. Your spacecraft was a time machine powered by gravity. This scenario was the basis for the movie Interstellar, and the physics was consulted on by Kip Thorne, a Nobel Prize-winning physicist. The depiction was accurate. On the water planet orbiting Gargantua, the black hole every hour on the surface corresponded to 7 years on Earth. That's extreme time dilation, but it's within what general relativity allows near supermassive black holes. The closer you are to the event horizon, the stronger the effect. At the horizon itself, time dilation becomes infinite. An outside observer would see you frozen, never quite reaching the horizon, your clock stopped, but from your perspective, you'd cross in finite time and fall toward the singularity. Black holes are the ultimate time machines to the future, but they come with a cost. You can't come back. Once you cross the horizon, you're inside. The future light cone, all paths forward in time point toward the singularity. There's no path that leads out. You travel to the future and die in the singularity shortly after. But if you stay just outside the horizon and then escape before crossing, you can use the black hole's time dilation to leap forward in time. This is possible. This is real physics. Let me end with a scenario. Suppose we build a spacecraft that can sustain 1g acceleration comfortable for humans, the same acceleration you feel standing on Earth. If you accelerate at 1g continuously, you'll approach the speed of light asymptotically. From your perspective on the ship, you'd experience constant 1g acceleration. You could walk around normally, time would feel normal. After 1 year of ship time, you'd be moving at about 77% the speed of light. But back on Earth, more than 1 year would have passed. The time dilation factor would have grown. By the end of that year, Earth's clocks would be ahead of yours by several months. Continue accelerating for 10 years of ship time, and you'd reach 99.9999% the speed of light. The time dilation factor would be enormous. Those 10 years for you would correspond to thousands of years on Earth. You could visit Earth in the year 12,000 AD, having aged only a decade. This is not science fiction. This is what special relativity predicts. The only barrier is engineering. We don't have engines that can sustain 1g acceleration for years. We don't have the energy, but the physics allows it. Time travel to the future is possible, and we're already doing it. Every satellite, every airplane, every fast-moving particle, all time travelers, all skipping forward through time at rates determined by their velocity and their position in gravitational fields. Time travel is not a future technology. It's present reality. We're all time travelers. We're all moving through time at different rates, some imperceptibly faster than others, some measurably so. The future is reachable, the past is not. And that asymmetry, the openness of the future, the closedness of the past, is built into the structure of space-time itself. Welcome to the universe where time travel is real. You're doing it right now.